Well, at the end of last time, we were talking about dictionaries. And I was talking about how great they are. And at this stage, what it seems as if their value really seems to come from the fact that you can index these things with seemingly arbitrary values, like a key, we call it. And the key has to be unique, just like indices for lists are unique. But unlike lists, you can index them with whatever, it seems. There are restrictions on what you can actually index them with, but I use this example of imagine storing student grades, right? Maybe instead of their names, they use their student numbers or their student email or something unique. And then with that unique key, I can assign a value. Great. And now I can access those things from the dictionary by indexing the dictionary with the keys. So there's my dictionary. I'll print the whole thing out, but I can look at Sally. And I can get the specific value, kind of like at Sally. Instead of indexing it with a number, I'm indexing it with a string here. But I can index it with other things. I can index it with, like they don't have to be strings, but you know, with strings. And then I showed you the example of why this is handy, because with the idea of imagine instead of a dictionary, I stored a student record. An individual student record is going to be stored as a list of length 2. Index 0 is the student's name, or maybe it should be like the student email address, whatever. But index 0 is a student name, and index 1 is their corresponding grade. So I can then, if I could store all of the students in that list, each student is stored as a list, and then I can store each student in a bigger list. So I have a list of lists. Well, really I have a list of references to other lists, but you know, for simplicity, list of lists. Can someone do me a favor and close that door back there? It's wide open. And there's nothing wrong with that. That's great. We're storing tabular data in this like tabular style format, right? We're storing it tabular, meaning like table. It's in the table. And you know, we've got a list of lists, one kind of like column. Even though it's a list of lists, we can sometimes think of it as like a two-dimensional list, like a table or a matrix, where like the one column is all the students' names, and then the next is their grades. Even though that's not really how we would index it, but that's how we can think about this thing. And if I asked you to find, well, do I have an activity here, or? Do I have an example? No. If I wanted to know a given student's grade, I would first need to do a linear search on the big list to find the internal list that contains that student's grade, right? So if I have a list of lists, the internal list is the student name and their grade, and the outside list is a list of those things. I have to go through each one until I find the student I'm looking for, and then when I do, then I can just get that student's grade by indexing it with the student at index 1. Just index that list, index 1. And we see here, I call the function linear search. Assuming this function exists, it just does a linear search. On my grades, I'm looking for Sally. It returns that student. Then I get the grade. That's the student at index 1. I print it out. I'm happy. Great. If I have 100 students in the course, how many things might I have to look at? 100. 200, 200. 5 million, 5 million. I got to look for each one. But with dictionaries, I don't need to do a linear search, right? I just looked up Sally. I just indexed the dictionary at Sally, like I did right here. So I didn't actually need to do a linear search. This is There, that's how it would work with looking it up in the dictionary. The dictionary eliminated the need for linear search. Now, going back to the previous topic, at the end of the previous topic, we talked about that like sum function. And you could use Python's built-in sum function to sum up the contents of a list. Add up all the values in a list and return their sum. Great. The good news is Python gave it to you for free, so you didn't need to write it. But if you wrote it, it would be doing a linear search. I mean, it's not really doing a linear search. I guess it's just going over each element one at a time. But that's how it would work. And even though I didn't need to write that function, when I call Python's sum function, it still had to get done. Python still needed to go and look at each individual thing. So even though I didn't write the code to do the summing, Python wrote that code for me and it would do the summing of all the things. So you might be tempted to think here, with the dictionary, it's going to be similar to that, right? Where, okay, fine, I didn't have to write the linear search. The dictionary just did it for me. No, it didn't. The dictionary doesn't need to do a linear search to find that thing. The dictionary can find your answer. Now, there's several asterisks attached to what I'm going to say. But for our purposes, the dictionary just knows where to look. If I have a class of 100 things, the dictionary takes 1 unit of time to give me the answer. If I double the size of the class, how much more work does a linear search need to do if I double the size of the input? Double. If I double the size of the input with using a dictionary, I still only have 1 unit of work. I don't double the amount of work. If I quadruple it, still constant time work. The amount of work the algorithm takes, the amount of time it takes to look up a value in a dictionary doesn't depend on the size of the input. It doesn't. So this is not a case of Python just doing all the work for you behind the scenes. This is an entirely different situation. And this, I'm not going to go into all the details now because this is outside the scope of this course, but dictionaries are phenomenal. Dictionaries are a data structure used commonly, as much as they can be, they're amazing. And they tend to be like the trick for speeding up your code quite a bit by making your algorithms a lot better. If you wrote code that took linear time, and the person sitting next to you wrote code that took constant time to achieve the same thing, they did way better than you did. No one wants your code. Everyone wants the code that takes less time. Because not only does it take less time, it uses less resources. You don't need to let it run. When your code's running, someone else's code isn't running. You're wasting electricity. No. You want code that can run in constant time if you can. But all of this comes back to, well, how the hell does it actually work? And I'm going to show you a high-level idea of how it works. And here's a common theme in programming. There's always these trade-offs of speed and space. All right? I'm going to draw very quickly. Here's my RAM. All right? Pretend it goes on forever. And remember how we thought about how lists were stored in RAM, right? How they're in this contiguous chunk of RAM. I mean, this is an idealized, traditional way of thinking. But with lists, the data is in some contiguous chunk of RAM, nicely and neatly. There we go. Let's just pretend that there's just some arbitrary right? Some giant chunk of RAM with, who knows, some arbitrary amount of space in between. But the whole thing with dictionaries comes down to this special thing called a hash function. All right? So here's how it works. You give me a key. And in this example, we were showing we use strings. And this hash function is going to magically turn that key into a number. Don't ask how, it's magic. But it turns it into some number. All right? And that number is going to be a memory address. So when you say, okay, Sally equals 88, we say, okay, all right, h of Sally comes back and it gives me the memory address, I don't know, right here. It doesn't really matter what the number is, it gives me a memory address. And in there we have the value 80, what was it, 88? 88. Then we ask for h of Jimmy. Was Jimmy one of them? No, Billy. And that magically gave us this one. Why? Don't worry about it. It's magic. It's a special function called a hash function that can take a key and turn it into a unique memory address. And Billy has 74. And then maybe I've got h of, I know it was like Jimmy Bob or something, right? But let's just say Jimmy. Jimmy, I don't know, there's hashed to here. And what was, Jimmy's crushing it, 99. And so on. Then, you want to know, so that's how I stored the data. Now you want to know, wait, what was Sally's grade? Well, all you have to do is throw Sally, that key, into the hash function. It gives you a memory address, and you immediately go look it up. There's no need to search. I don't need to start searching through elements. No. It's a lookup table, basically. Sally. And when I give the hash function Sally, it gives me exactly where to go find it. Now, the downside with something like this is it takes up a lot of space. The amount of actual information stored is probably going to be a smaller proportion of the amount of space that's actually been allocated for it. But I can look up the answer like that. Way better. That's amazing. It's unbelievable. So this is the idea of hashing. And if I go to some dictionary, what? And I try to hash it with something like a list, it's going to say something saying unhashable type list. That's because Python doesn't know how to hash a list. It knows how to hash other types. In fact, it knows how to hash tuples. So you can do it with tuples just fine. But it's all based on hashing. Any questions about this? This high-level idea is outside the scope of the course. So the nuance and details of how this actually works, not important right now. All right? But I think it's pretty damn neat that you can store information and look it up in constant time. No need to go searching through records to find it. You just look up with your magic hash function and it tells you exactly where to find it. Any questions about this? Yeah?
So Billy's grade goes
Yep, all I do is I go, okay, Billy, 74, I go look up to that memory address and I just update the value at that memory address. Absolutely, good call. Other questions about it? Now this is this is assuming we have something called an idealized perfect hash function, that this hash function will magically map everything to a unique thing. That's not possible. It's impossible. There's an infinite number of things that could be hashed, but there's only a finite amount of memory addresses, right? So you're going to have what we call like a collision, but we have ways of dealing with that, so it's not too important right now. That's outside the scope of this course. That's outside the scope of next semester too. I'm just giving you a little brief little idea of what's going on. If you can, use the dictionary. It's way better. Other thoughts, concerns, comments about this? Now the next thing we'll talk about is, excuse me, are sets. And here's a way to make a set. What's neat about a set is it'll only ever allow you to have one, like if you have a nice, good, clean set, you'll only ever have one copy of each value in a set. Great. And the way the sets are actually going to be done is with a dictionary. Basically, if something exists, basically it's a dictionary where the value that's being stored is like true, or it's whatever, it's arbitrary, it doesn't matter, just that key needs to exist. So a set really is just a dictionary, that's all. In fact, in like Java, when you make a set, you'll call it like a hash set, because it's like you call dictionaries hash maps. It's a map from a key to a value. It's a dictionary. It's done with hashing. So we have sets, and what's neat about a set is you can make it like this, and yeah, notice although we included Frank twice, it's only going to ever exist in the set once. And what's neat, because this is a dictionary, if I want to check if something exists within the set, it's a constant time lookup. There's no need to search the set to see if something exists. No, constant time lookup. That's amazing. And the order of the elements really doesn't matter for a set. Sets really don't actually have an order associated with them. Python will kind of try to preserve any ordering you give to it, but by definition, there really is no order to a set. Now imagine I had two things here, right? I had a set that was the name of the students taking 161, and then the name of the students taking Math 106. So I have two sets. And with this, I can ask some really nice simple questions that might be handy. For example, I can ask, who is taking both courses? Does anyone know what we call it if I have two sets and I want to know where they, like what's common between them? Does anyone know what we call that? Intersection. Who said that? Well done. Intersection. Yeah. First of all, I can use the in to check if something's in there. But here we go. Union, intersection, and difference. We'll start with union. That's union. I want to know who's taking Math 106 or 160, Computer Science 161. That's the union. That is everything in both. It ignores duplicates. It's just everything in both. That's the union. You'll notice union is kind of like an OR. Union might remind you of like a logical OR. It doesn't matter if they're in both or one or the other. It's just if we get it either way. And then there's the intersection. That's this. Tell me who's taking both. The intersection is more like an and. They have to be in both. Who's taking 161 and Math 106, right? So it'll only tell you those that are in both. And then there's set difference, which is who's in one but not in the other. right? So here, only taking computer science, right? So it's, well, who is in 161 but not in Math 106? There you go. You could do a set difference. So set's pretty handy. So here's an activity. We'll just talk about this one real quick. Imagine I gave you the text from a book that you could load up into Python. All right? Some arbitrary book. Could be your favorite book. I don't care. Because strings can be huge, right? And if you want to know, if I ask you the question, how many unique words are there into this book, in this book, the easiest way to answer that is put all the words into a set and then tell me the size of the set. Any duplicate words are ignored. You don't count duplicates. Duplicates only get represented once. So the set would contain all of the unique words in that book. And then if you want to know how many there are, well, how big is it? Cool. Then if I gave you another book and said, what books do they have in common? Well, I can just, what's the intersection? What words exist in both books? Not only in one or the other, but which words are in both books? You could do intersection of the two books. I wanted to know the number of unique words that exist between the two books. Well, I guess I could get the size of the union of the two. And then what if I wanted to know which words are in one book and not the other? Well, I could do set difference. What books are in that book but not that book? Sets are a great, easy way to do this. So first of all, sets are built on top of dictionaries, which are quick. They're fast. They're computationally very efficient. And they provide really easy operators for asking questions kind of like this. If you're thinking to yourself, that seems rather like special purpose. Yeah, absolutely it is. A list is a very general purpose data structure. Sets, they're not really general purpose. They have their purpose. It's a tool that's really damn good at doing its job. If you need to do that job, grab the right tool for the job. You could answer all of these questions with lists. You could. But it would be a pain in the ass to implement, and it's going to be computationally slow. There's another tool you could use, sets, that are way better tuned for that job, and they're really good at it. But they're really only good at that job. You're not going to use a set for some arbitrary other thing. So it's a special purpose tool for a special job. A list is a much more general purpose tool that's good in general. You just always pick the right tool for the job. So if you're thinking, yeah, like I think I could count probably on one hand, maybe two hands, the number of times I've used sets. But when I do, I'm sure as hell happy they exist because it makes my life a lot easier. Any questions about sets? Why is everyone leaving? All the doors are open to this lecture hall for some reason. All right, so. Raise your hand if you've ever made a bug in your code. Of course you have. At this stage, you've written several algorithms, whether you like it or not. You're probably pretty comfortable with those assertion tests now, and if you're not, that's your fault, not mine. You should be writing them. But we've likely had more bugs than working code. Raise your hand if you would say, chances are I've probably had broken code more often than I have correct code. Yes, because that's programming, right? So first and foremost, you're normal. If you didn't raise your hand, you're either lying or you've gotten really lucky. Debugging. It would be weird if you didn't have bugs. Remember, your code's going to be wrong every time you run it before it's right. It only needs to be right once. It could be wrong 1,000,000 times before it's right. And then once it's right, you're happy, right? So before getting started, it's important to emphasize what this is all about. It's not about getting your programs to work. When your code isn't working correctly, obviously the ultimate goal is to get it working correctly. But that's not a great strategy for debugging. The strategy for debugging shouldn't be to get the code working. It should be to understand why it's not working. And it might sound like I'm saying the same thing. I'm really not. The goal isn't to get it working. It's to understand why it's not working. And if you're understanding why it's not working, you can understand why it's behaving the way it is. And then you can figure out, well, where's the alignment issue? It's doing, whenever you hit run, the code's doing exactly what you told it to do. So if you've been blaming the computer, I've got bad news. So every time you hit run, the code does exactly what you told it to do. So when we're in lab and you call me over and you're like, my code's not working, and I say, well, explain to me what it's doing, and you go, well, I don't know. I'm going to walk away from you because I can't start to help you. That's a waste of both of our time. When it doesn't work, that's when you start working. That's when you start going, okay, what is it doing? So you need to understand what it's doing and why it's doing that. And you need to know, if you're programming the correct way, I give you a problem. First step, understand the problem. Step 2, come up with a way to solve it. Step 3, start writing code. Step 4, your code's obviously broken. It's never going to work right the first time. So find out why it's not working. Maybe your original idea of how to solve the problem was wrong. Or maybe it was right, but you implemented it wrong. Either way, it's either telling you you need to go back and rework how you want to solve the problem, or you need to change your code so it actually does what you want it to do. Either way, it's up to you. When you write code, and it's getting at the point of the semester where earlier in the semester, I could walk by, look over your shoulder, and I can immediately see everything wrong with your code. We're getting deep enough into the semester where that's not happening anymore. So when you go like, I don't know, I'm sorry, I can't get it working. It's going to take me more time to walk over to you, sit down, look at your code, try to understand what the hell's going on, than it is for you to just look at your code and be like, what the hell did I write? That's not saying don't ask for help. No. That's not what I'm saying at all. What I'm saying is don't skip the step. If you're getting me to debug all your code or the TA to debug all your code, you're not going to be successful because that's programming. You want to get credit for a computer science course without debugging? Debugging's programming. So get debugging. Get used to it. It's a good thing. That's where you're going to learn all this stuff. All of this is to say, you're going to be wrong all the time. And I've been saying it since the beginning of the semester. And raise your hand if at this point in time, we're a little more than halfway through the semester, if at this point in time you continue to agree, or you know enough to say, yeah, he was right, you're going to be wrong all the time, and it's all about debugging. Yeah, of course. Of course that's the case. So get used to it, and that's okay. If you get it wrong and you get frustrated, get used to it. I get it, it's frustrating, but that's the process. That's why the programmers are paid the big bucks. It's why they're all bald. They pulled their hair out already, right? So, debugging. Our programs grow in complexity. First and foremost, the easiest way to debug is don't introduce them in the first place, which I realize is such a stupid thing to say. But there are programming strategies you can start with that helps to eliminate a lot of bugs to begin with. We've talked about a lot as we go. Break your problem down into smaller bits, write a lot of functions, test those functions. If those functions work correctly, you're safe to use them in bigger functions, etc. That is going to eliminate a lot of bugs. It's easy. It's a lot easier to write small functions and test them, and then use those tested smaller functions to solve a bigger problem, than it is to write a lot of code to solve a bigger problem and then go, where is it wrong? I'm certain you know exactly what I mean by this stage. Treating your data structures as if they're immutable, that helps a lot. There's a lot of things you can do. Write a little bit, test frequently. There's a lot you can do to hedge against bugs in the first place, but you're going to get bugs. And as the code gets more and more complex, you're going to get more and more bugs. And those bugs get more and more difficult to find. But if you've got really nice and well-designed code, you can eliminate a lot of those bugs to begin with. Because, and maybe not quite at this stage, it might not make a lot of sense, but if I'm telling you to go solve a problem, and you've got like, well, this function depends on that function, which calls this function, but this function requires information from that function, which also needs information from the original function, which is good because we called it first, and then we can pass the information over there, and this one has a side effect that stores data. If you've got that crazy web of interacting stuff versus, okay, this function's called, it returns a value, and then this function is called and it returns a value, and then the sum of those two things is passed to this function, it returns a value, and then this here. If your system is designed like that crazy spaghetti, or this nice, like, flow of this to here, get it back, and then this to there, get it back, one of those two things are going to be a lot easier to work with. So more motivation for taking the time and thinking about how you want to design your code, because those decisions will pay dividends in the long run for eliminating the amount of pain and suffering you have to do with debugging. But no matter how much of that you do, you're going to have bugs. It's the way it is. No matter how good of a programmer you are, you're going to have bugs. Beyond the obvious benefit of fixing your code, debugging has other important aspects to it too. It gives you a better understanding of the algorithms you're working with, a lot better. It gives you a lot of knowledge of the programming language. It gives you good problem-solving skills. It gives you a nice, good system and strategy for just getting more experience, thinking logically, step by step, what's going on. And it gives you more experience just thinking about the execution flow of your program and where the data is moving around. So not only, like, when you're debugging, you're not just when you're writing code for an assignment and you make a mistake, when you do the assignment, you got to remember, I'm not making you do assignments because I want you to write a zombie apocalypse for me. I hate to say, I really don't care about your zombie apocalypse, okay? What I want you to do is I want you to code it so you learn something, so you actually do it. You've got a complex problem and you implement it and you solve it. And I know you're going to mess it up. Raise your hand if you've worked on assignment 2. Raise your hand if you've had bugs so far. Yeah, obviously. When you're going through and you're debugging, that's part of the assignment, right? That's part of your job. Getting that experience to debug is the point of the assignment. In fact, assignment 3, most of assignments 3's emphasis is on debugging. So get really ready for your code to be wrong and get mad. But just know that's the point. Sometimes people will come to me and they'll say, oh, I've spent hours working on my assignment and I just can't get it working. And I'm like, well, how long? They're like, I spent like 2 hours on it. And I go like, if you were writing an essay for a course and you went to your prof and you said, I spent 2 hours working on this essay, they're going to laugh you out of the room. And you think you could say that to me and that's a normal thing? These assignments are going to take you hours. If the stars align, maybe you get it done in 4. Maybe. Raise your hand if assignment 1 took you longer than 4 hours. Raise your hand if you're done assignment 2. Raise your hand if you've maybe spent more than 4 hours with assignment 2. And I'm not just counting time of like sitting down and actually programming. You got to remember, here's an aside. Here's one of my biggest tips for you when working on assignment. You know how I say step 0 of the assignment, read the assignment and understand it? Yeah. That's not just a throwaway statement. Here's how I did all my assignments in undergrad. I'd get the assignment and I would read it immediately. And then I'd think about it. And I would say to myself, I'm not going to sit down and write a single line of code for at least a week. I'm just going to think about it. Maybe I'm walking to work, I'm thinking about it. I'm in the shower, I'm thinking about it. I'm watching baseball, I'm thinking about it. I did most of my PhD in the shower, I swear to God. That's where I got all my work done. The problem, understanding the problem and coming up with a solution doesn't happen at a keyboard. So remember that. Do yourself a big favor, think of the assignment and just think about it. You don't have, and when I say think about it, I don't mean sit down in your room and go, what am I going to do? No, that's not how it works. No, you passively think about it. You go to the gym, you're thinking about it a little bit. So there's a good strategy there. But these assignments are going to take a while. You're going to have a lot of bugs. Get used to it. That's the point. Because debugging gives you all of those skills. Any questions so far, by the way? Better plug my computer in. Everyone's good? Everyone's happy? Or as happy as you can be talking about bugs? All right, so sometimes we get lucky. And actually, it's a lot better now than it used to be. But in many cases, Python will have error messages like this. Right? You'll see something like this. Who here has seen an error message similar like this where it kind of tells you there's a mistake and it kind of shows you where? Yeah, it's kind of nice, isn't it? So sometimes bugs are relatively simple to address. Python even tells you exactly where it is. Right? It shows you right there. And it even says on line 17 in that statement, and right here, there's invalid syntax. Now sometimes the error messages aren't that helpful. But sometimes they are literally as helpful as like, here's your mistake right here. And some IDEs, like your programming environments, will even like correct them for you. It's nice. But sometimes you're going to get an error message. Python will give you an error message with some types of bugs. It'll give you an error message, and it's a little more cryptic. It's hard to understand. But the good news is, these bugs don't happen in isolation. Someone else has seen this bug. Copy it, paste it into Google, see what you get. Sometimes it'll tell you, someone will be like, I had this bug, and then someone will show up and be like, oh, you just need to do A, B, C, X, Y, Z, and you're good to go. You do it, and it worked. Has anyone done that yet? Where they copy and pasted an error message into Google. You see, someone else has a problem, and the solution is, oh, do this. And then you do that, and it worked. Great. You're a really good programmer if you're doing that. And here's actually why that's a very good important skill to do and develop, is you know what you want to do. You know the code you wrote, hopefully. You hit run, you get an error message. You don't know what it is. You copy it, you paste it, and you see someone else with the same problem as you. Chances are, you know, we're getting to the stage of the semester where you're not going to be able to know immediately what the other person was trying to do when they got their error message. But you know enough that maybe they've posted their code, a couple lines of code, and the error message. And you know what you wanted to do, and you look at their code, and you can figure out what they were trying to do and where the context of their bug came up. So you know the problem you have. You know that they're having the same-ish problem as you. You can understand the code they posted enough and understand the solution enough that you can implement it yourself. There's a lot you got to understand in order for that to work. So if you've ever thought to yourself, oh, I copied the paste the error message in and I got a solution, haha, amazing, good for me, that actually took a lot of skill on your part to do that. So very good. But this is a skill to develop. Common error messages you'll see are things like syntax error, indentation error, name error, type error, index error. Chances are you've had all or nearly all of these bugs by this stage. Syntax errors. These ones usually produce error messages that are pretty helpful. It tells you usually where the error is, as seen in like the above example. And there's really not much of a debugging strategy for this because you just kind of do what it says, right? So here's an example. Who can spot error messages here? Or error messages. Who can spot some issues here? And you know what? Let's do this. Oh, it was never closed. Oh yeah, I messed up, right? See, look, it's telling me though, right? Invalid syntax, oh, look, maybe, yeah. Oh, expected the colon, look at that. Invalid syntax, what, oh, I can't do plus and multi, I guess, okay, all right, yeah, that was my mistake. Name broken is not defined. What are you talking about? It's right there. Oh, it's Borken. All right, there. And then walrus is not defined. What's this walrus? Yeah, what does that do in there? Oh, it worked. Thank God, finally. All right, good. Right? Raise your hand if you've ever played that game before. Kind of like whack-a-mole with your error syntax messages. Yeah, of course you have, right? We've all done it. Great. Type errors. So Python's pretty good at figuring out types most of the time, but Python can only do so much. Python can't suddenly figure out what it means to add an integer and a string together. So here, when I say a equals 5, Python goes, well, okay, 5 is an integer, so a is going to be the integer 5. B is 5.5. Well, 5.5, it's a decimal, it's clearly a floating point number, so I'm going to store to be the floating point number 5.5. And then when I say a plus b, well, okay, you're mixing types. You're adding an integer and a float, but I can do that. And so 5 plus 5.5, well, that'll be 10.5. The result C will have to be a float because one of those two values was a float. So in order to retain that decimal value, we need to make sure C is a float. But Python's doing a lot of figuring out for us, right? So it was okay figuring out an integer plus a floating point number. Fine. But if I say hello divided by 32, it's not going to work. If I try to say 99 plus bottles of beer on the wall, it's not going to work. Because it's saying, well, hold on. I know what it means to add two numbers together. I know what it means to add two strings together. I know what it means to add two lists together. I don't know what you mean when you say you want to add a number and a string. I don't know. Maybe you want to convert that integer to a string and then concatenate it as if it was a string. Maybe you do, but I don't know. If it is what you want to do, then do it. Make it a string and concatenate it. But as far as Python's concerned, it can't make that assumption. And if you're thinking to yourself, well, why wouldn't it just figure that out? You know, it should be able to figure that one out. Well, be careful, because as you learn more and more and more about programming, just because the programmer wrote it doesn't mean the programmer meant it. Okay? So even though 99 plus bottles of beer on the wall, just because you wrote it doesn't mean you really meant it. So Python was going like, I'm not sure you really meant this. So if you really want to add these things together, just do it the right way by converting it to a string or using that f string thing I showed you before. So Python is only going to make so many assumptions. And sometimes when it makes assumptions, it'll be wrong, which is another cause of type issues. But these are type issues. Sometimes we can have an issue created by types that don't generate type messages. Consider the inconsistent function defined in the below example. There is nothing wrong with this code, right? There's no mistake. And if I run it with that right there, inconsistent 1, 1, 2 integers, it gives me back the integer 2, right? There's going to be no error message generated, no nothing. Nope, looks good to me. But if I run that exact same function with 2 strings, 1 and 1, I get back the string 11. It's not going to generate an error message. It did exactly what you told it to do. So this would be an example of a type error that didn't generate an error message, but the problem originated by the fact that you, the programmer, mixed up these types. Okay? And these type errors are kind of easy to make in Python, which is one of the bigger things I dislike about Python, is how easy it is to make type errors like this in Python. Other programming languages, it's a lot harder to make these mistakes. Python is happy to make this mistake, and it'll carry on and smile at you as it does it. Like, here you go. It's 11, right? And you might say, well, then just don't pass it as a string. But how many of you have read input and forgot to convert it to an integer? Yeah. Those mistakes happen a lot. It may seem obvious that you shouldn't call the function with the wrong argument types, but yeah, input. How many times have you made a mistake? Yeah, exactly. All right, logic errors. We'll stop here because this is the big bit here. Any questions? All right, I'll see y'all later.